Okay, so it seems that we have already started. Good evening, everyone. My name is Lukáš Kačena. I'm from prg.ai, and it's my great honor to welcome you all here. We at prg.ai, Murray, you maybe don't know, we were established in 2019, so before all this AI hype, and we are basically taking care of the Prague AI ecosystem. So please, Murray, let me introduce you the prg.ai community. Prg.ai community, Murray Campbell, our honorable guest. Thank you. If you organize such an event, you basically have two questions. Will the speaker arrive? And will people come? So it's great that both delivered. We are happy to see you all here. We have people from academia here. We have people from startups. We have people from corporates. And we even have people from the government. Dane, yeah, I saw you. So it's a nice mixture, various sectors. And always the prg.ai meetup is about enjoying the opportunity to meet your old friends, to make new bonds, to make new connections, to initiate collaborations, and of course to enjoy the evening as such. Fortunately, I'm not here to do the talking, but before I hand over to Murray, I just would like to thank first to Josef Šivec, his team, and the Alice project that actually helped us with organizing this meetup and financially supporting it, to Faculty of Information Technologies for actually providing us with the venue, to Martin Schmidt and Equilibre Technologies for bringing Murray here, and thank you, Murray, for being brought here, actually, for giving us your time. And thank you to Bára Pelcová and prg.ai team for organizing the event. Well, let's move on to Murray's talk. Once again, Murray, thank you very much for coming. I'll just briefly introduce you, and I hope I have everything right. Murray Campbell is a distinguished research scientist in the exploratory group at the IBM T.J. Watson Research Center. His current research focuses on methods for evaluating the capabilities of AI systems, neurosymbolic approaches to AI, and brain-inspired AI architectures. In his first project at IBM Research, Murray was a member of the team that developed Deep Blue, the first computer to defeat the reigning world chess champion in a regulation match. And I read that you actually love chess, so it's a surprise.
Yes.
During Murray's talk, you can use Mentimeter, you can use the QR code, or you can go to menti.com and use the number code that you can see, 33881735, and you can ask him the questions, and we will see how it goes. Maybe Murray can take the question during his talk, and there will be a Q&A session at the end. So that's all from me now, and the floor is yours.
Thank you. So it's great to be back in Prague. It's been more than 25 years since I was here, so I'm glad to be back. I actually made it a 3-4. Here I was at ML Prague, and I was visiting my buddies from ex-IBM buddies, now at Equilibre as well, Martin and his friends. So today I'd like to talk about the role of games in AI. The role of games has changed quite a bit over the decades since they were first proposed. So I'll give my view of the history of this, and then suggest a few directions for how games can play a role in AI going forward. Before I dive in, I'm just going to give you some of my earliest experiences with AI and games. So my first recollection of seeing a computer play chess was in the movie 2001: A Space Odyssey. I can remember seeing this movie when I was a kid and coming out of the movie going, oh, what was that? But besides all those mind-blowing graphic sequences, which were amazing for the day, I noted that a computer was playing chess in the movie. And in fact, it beat one of the astronauts quite easily. In those days, I was also a Star Trek fan. And I saw this scene where Spock was able to beat the computer at this weird form of 3D chess. In fact, one of the plot points here was that the fact that he was able to beat the computer meant there was something wrong with the computer, because he had programmed it, and therefore every game should end in a draw. Now, he obviously didn't understand what was going on, or the script writers didn't. That's quite illogical for him to have said that. My first real-life exposure to chess, games and AI, really, was I think it was in 1974. I was a high school student, and I was visiting the University of Alberta, where I ended up getting my bachelor's and master's degree. And I was attending an open house for the computing science department. And in a back room, in a corner of the floor where the computer science department was situated, there was a lab that was open, and in the back corner of one of the labs was a machine that looked just like this. It was a PDP 1145, I believe. And on it was it was playing a game of chess. It had a program on it called T-Bell, which was presumably Tinkerbell, programmed by Ken Thompson, who went on to great fame as a Turing Award winner and so on. And T-Bell actually grew up as well. It became the chess machine Bell, which ended up winning the World Computer Chess Championships later on. So when I saw that computer playing that that game, I was kind of hooked, because I was a chess player at the time, provincial level champion sort of. But it was clear I was never going to be world class, and so I was already thinking about programming a computer to play chess. So, here we go. So this is 20 years later, after that event, more than 20 years after I first saw a computer playing chess for real. I was sitting across from Garry Kasparov, and here I'm making a move in what turned out to be a very critical game in that match, the second game in the 1997 match, which Deep Blue would go on to win in very nice style. And eventually, in the last game of the match, spoiler alert, it won. So here's a quick outline of what I'd like to cover. First, I'll talk about the issue of what is a game. And it turns out it's amazingly difficult to define a game in any consistent way. And then an easier question, really, why games? Why are games useful for AI research? And I'll give you my thoughts on that. But there's any AI researcher who's done research in games will have a list of reasons they use to justify it to the funding agencies or whatever. Following that, I'll give a quick summary of the major eras in AI in games. There's quite distinct areas of this. And then I'll wrap up with some directions which I think we should pay attention to for AI research, and where games can continue to have a very significant role. So, what is a game anyway? You start to worry when somebody like Wittgenstein says you will not find something common to all games. That means it's going to be probably quite difficult to come up with a definition. But maybe we can come up with a working definition for AI researchers that is useful, even if it doesn't cover everything that the common sense of games provides. Here's another definition that I kind of like. The voluntary attempt to overcome unnecessary obstacles. Now you think about that. You create an artificial context where you put obstacles in the way of doing whatever it is you want to do, and then you have to overcome them by some clever means. That's an interesting way of thinking about a game. And the players agree that they're going to let these rules, these unnecessary obstacles, guide the way that they act in that world. But I think something's missing there. And so this other definition from Sid Meier captures part of what's missing anyway. So games are a series of interesting decisions. Now that's clearly not specific to games, but I think it captures the element that we're missing. But if you think about, for example, if I gave you a game, I gave you two numbers and divide one number into the other, well, that's a series of decisions, probably not that interesting, and that's why long division isn't considered much of a game. So while I won't give a precise definition of game here, from an AI point of view, there's a few elements that are important. There are a set of rules that limit the actions, so that's the unnecessary obstacles part of the definition. Typically there's goals in the game, things that you are striving for, or the players are striving for. I'm not excluding single-player games here, or puzzles, or whatever you want to call them. I think both are equally interesting. And on the interesting side of the equation, I would say that here's a couple of ways where why games can be interesting. They involve informed decisions. You maybe don't have all the information you need, but you at least have some information on which to base your decision. And the better players are better at using that information to make good decisions. And a game is often interesting because it involves some sorts of trade-offs. You can get a benefit in one way, but a negative effect in another way, and you have to decide which is going to make the most difference in the end. They say that chess is interesting and has had such great longevity because of the trade-off between bishops and knights. For those who play chess, bishops and knights are supposed to be 3 points each with maybe a little edge to the bishops. But the good players know how to trade off, when to trade off and get two knights or a knight and a bishop. So that's an element that I think is important for games. So why games for AI? I'll only give a partial answer here. I think this book, which is a nice book, actually devotes 8 pages to this exact question. Why games for AI? Before I dive in, let me just give you some statistics which I think are quite interesting. The red line in this graph is the number of academic papers published by decade that includes the search term artificial intelligence. So you can see that the red line is going up, as you'd expect, but of course note that it's a log scale. So as we look at the number of papers coming out, it seems to be growing exponentially. It is. It is growing exponentially. So you can see that the number of AI papers is going up. The blue line is the number of AI papers that mention games. And you can see that that's also going up exponentially, although there's a little more structure to that one, as you can see. And then the green line is the percentage of all AI papers that mention games. And so, interestingly, in the early days, the AI researchers of the 1950s and 1960s were very much interested in doing games, particularly very simple games, because that's about all they could do, to be honest. There wasn't much else that the computers of the day could do, given the lack of processing capability. Then you can see there's a big trough in the 80s, 90s. That corresponds, I believe, to the expert system era, where people were trying to build rule-based systems, and games just didn't fit into that. They were trying to do chemistry or a virtual doctor or whatever. And games were seriously understudied in those decades. And it started to come back after Deep Blue, and as you can see, throughout the 2000s, there was a peak, actually even higher than the peak back in the 60s and 70s. I think this is largely because of the work of companies like DeepMind with their Atari and later AlphaGo and AlphaZero and so on, and work on poker that came later by others. So, and then I think the only reason it's dropped now is because of the maniacal focus on LLMs. So LLMs aren't particularly good at games, and so nobody even tries. So I think that's a possible explanation for that slight dip. All right, so my typical answers for why games for AI. Games can exercise many different aspects of an AI system. Learning, reasoning, perception, and so on. We'll come back to this in a little bit. Games tend to be very practical in many ways. They don't require a large gathering of data sets, although in some cases that isn't true. But they also can get the interest of the general public. So if you're looking for an exciting application that people will pay attention to, games are interesting. And games allow us to follow the scientific process where we start off with making a lot of simplifying assumptions and develop a system that can perform with those simplifying assumptions, and then start relaxing those assumptions, adding some complexity in a very controlled way. And games allow us to do that quite nicely. Let me just show you what I mean here. Take, for example, chess. Excuse me 1 second here. So chess is normally described as a two-player, zero-sum game of perfect information. And I hope you can see those labels there. Yeah, I think you can. So as we can see illustrated here, chess actually makes a lot of simplifying assumptions. In spite of the fact that everybody, throughout history has considered playing chess well as a sign of great intelligence, chess is an environment for AI systems is actually extremely simple in all but one aspect. If you look at it's only two agents, but it's zero sum. So two agents, zero sum is a very simple form that, it's easy to understand via Minimax. The payoff structure is very clear. There's wins, draws, and losses, and very clear definitions of what constitutes a win, a draw, and a loss. It's fully observable. You can see everything. Everything you need to make a decision is right there in front of you. So you should be able to do it. And so on this scale of, red is easy, green is easy, yellow is medium, red is hard, like real life. Chess is pretty low on those three aspects. I would say it's combinatorially complex. It's a large state space. It's very discrete, so that just changes, a small change in a position can cause a big change in the evaluation. So you have to conduct a search through this combinatorial space, and so it becomes hard just for that reason. But it's nowhere as hard as real life, where there's a much larger state space involved. But that was even misleading. If I have a much longer list of simplifying assumptions, you can see there, and I won't go through them all now, but I'm happy to, when we come back to them, answer some questions about the, excuse me. But these are a partial list of some of the assumptions that chess makes to simplify the task. And you can see it's pretty much pegged right in the green with just a few exceptions like the state space, as I mentioned, but delayed rewards. You don't know what your mistake was. And, well, you know at the end of the game you made a mistake, but the credit assignment problem is very difficult. You don't know exactly where the mistake was. And that makes chess hard as well. But even that doesn't go too far into the yellow. So now I'll move on to a brief historical perspective on AI in games. The hope is, as we go through this, it'll provide some insight as to future research directions. So I'm following the approach that was taken in Donskoy and Schaefer, a paper from way back in '89. Excuse me. I've been talking a lot today, so I'm starting to lose my voice a little bit. So hopefully it'll hang on for another hour. So they divided the history of AI in games into three eras, and I added the learning era, which came after their paper. I'll spend most time on the early eras because I think the learning era is familiar to mostly to this audience, and in fact, many of you were born in the learning era, so weren't even born in the earlier eras. So at the beginning of the pioneering era, we have Claude Shannon laying out the case for games and AI, although AI as a term hadn't been invented yet. And work in this era was primarily around just getting machines to play games at all. I think the first computer that could actually play chess, the full game of chess, was 1957, a program developed by Alex Bernstein at IBM, in fact. Another feature of this era was very naive optimism. Two of the pioneers in AI, Newell and Simon, pictured here, made some outlandish predictions about how easy it was to create intelligence and that computers would be the world chess champion very soon and so on. Obviously, they were extremely wrong. It's interesting to think about what they misunderstood. But we can discuss that later if you're interested in talking about that. In 1959, again at IBM, Arthur Samuel came up with a checkers program that was better than he was. And he actually coined the term machine learning at that time. And the fact that the machine beat him, probably the scriptwriters in Star Trek weren't quite aware of that landmark. This quote, which I won't go through in detail, from Alan Newell, explains to some extent why the researchers thought chess would be perhaps more important than it ended up being for the mainstream of AI. And clearly, when humans play chess, they use a lot of very clear cognitive capabilities, memory and reasoning and planning and so on. And turns out that computers don't need to do any of that. They can do a much simpler process. And so chess turned out not to be the best domain for at least human emulation of machine learning. The technology era, which came after the pioneering era, is perhaps a little less interesting from the modern point of view. I think of it as the bitter lesson era. If you think of Rich Sutton's argument, people of this era decided they were going to give up on trying to emulate human chess programs and would just simply search as quickly as they could and as simply as they could and use computers for what they do best, which is calculating, and it just worked much better. The algorithms era, I would include Deep Blue in this, as well as some work on Chinook, the first checkers program that won the world championship. I think it was an improvement on the algorithms for searching and evaluating chess or checkers positions. And the programs became much stronger in this era, partly because of technology, but also partly because of the algorithms. And that trend continued for a decade or more after that, as some chess programs became extremely strong, superhuman, even running on a PC in those eras. Okay, and then of course the learning era is well known at this point. As I mentioned, Atari, AlphaGo, and University of Alberta, and CMU in poker. There's OpenAI did Dota. So I think a lot of things have happened since that time. I think, interestingly, to the best of my knowledge, the best current chess program is Stockfish, which is not using the AlphaZero model, but it is taking the sort of the classic Deep Blue style model and extending it in various ways, including with neural networks for evaluation. So I think that's an interesting trend. And it's always interesting to mention this one outlier on this whole trend, and that's the work of Jerry Tesaro, who a colleague of mine at IBM, who back in the early 90s built a backgammon program that was completely self-taught and played at or near world champion level using the hardware and the tools of 1990. So I think that was an impressive piece of work. And it's interesting to think about what comes next. I think learning will continue to be important if we look at games. But I'm thinking we're sort of running into problems, and we'll get to that in a bit, problems that are difficult for purely neural systems. Clearly, Go was not tackled by a purely neural system. It was tackled by a neurosymbolic system. There was a Monte Carlo tree search combined with neural networks that helped with the evaluation and move ordering and sort and so on. So I like to think about how LLMs or transformer-based systems can be relevant. I think they can. This is something maybe we can discuss in the questions section. But there's lots of interesting thoughts there. So let's go through 3 ways that I think games are still useful for AI. One is on human AI collaboration, games that involve that. And I just want to show you this quick case study. I'll breeze through it fairly quickly, but I'd be happy to come back to this because I've spent a bit of time thinking about this. So let me just get a little closer so I can see the charts a little more clearly. You can imagine 4 different eras here where in the first phase you have a system that can play the game. This is imagining you're having an AI system working together with a human trying to make a decision in a game. And in this case, I'm talking about computer chess, and particularly classical computer chess, so roughly 3 minutes a move, and I'll show how it scales in other directions later. In phase 1, computers are really too weak to provide much help to a high-rated player, and any attempt to use them would just be a distraction, so they're basically get ignored, human solo. Then in phase 2, you get the human-led phase, where computers are not strong enough overall to help, but they have some special capabilities that, for example, in chess, their tactical calculating ability that allows them to do particularly well. Kasparov defined a game he called advanced chess, which was a grandmaster and a computer against another grandmaster and a computer. And he participated in some of those exhibition matches. Phase 3 is when the computers become significantly better than a strong human, but they have gaps in their knowledge or their capabilities that primarily, so the model of collaboration would be you would primarily go with the computer move, but if you saw a situation that mapped into one of the known weaknesses, you may overrule the computer, or you may say take the second best choice because you know you're avoiding a particular situation it doesn't quite understand. And then it's majority computer-led. And phase 4, which is where we are now, the level of computer play is so high that any attempt by a human to alter the play of the computer would just get in the way and cause trouble. So the best thing to do is just hands off. Just let it choose its moves. So look at this graph. I think it's quite interesting. On the x-axis is the year, and on the y-axis is the chess rating. And you don't need to know any details about that other than higher up is better. And so the blue line is the rating of the best human in the world at the time. And you can see it's been relatively stable. It's gone up somewhat. Most of this time is either Kasparov or the current world champion, Magnus Carlsen, has been number 1. So that fills out most of this chart here. The green line is the rating of the top computers. And you can see that are initially below, and then moved above, and then moved way above. And the red line is, the red line is the estimated performance of the best collaborative system, human and machine working together. And you can see, I've tried to map it onto the areas that the phases that I talked about. So there was the solo human phase, the human-led phase, the computer-led phase, and then finally the computer solo phase. And you can see we went through all of those phases in classical computer chess. So you may ask, as you see this chart, you see this, there's a big difference in ratings between the best human, 2,800, and the best computer, 3,600 or so. I just want to convince you of that gap is absolutely huge. Just by a quick example, I apologize to the non-chess players, but I don't think you really need to understand chess well to get this. So this is a position from game 2 that I remember I showed you a picture of myself making a move. This is that same game, many moves later. And in this position, Deep Blue played the move bishop to e4, which was considered brilliant at the time. And the move is shown by the red arrow here. To a good player, it seems like a good idea because it snuffs out all Black's counterplay. That means Black doesn't have any chances to make a mess, and he just has to suffer until he loses, more or less. And then the other move in the position to consider is queen to b6, and that seems to win more easily, at least to the computers at the time. And Deep Blue originally was going to play queen b6, and then it switched to bishop e4, which it considered a little bit better. And at the time, it was thought that no other computers could play the move bishop e4, but a few years later, it wasn't too long, a couple of years, other chess programs were able to play that move. Interestingly, a few years after that, it was discovered that, in fact, bishop e4 wasn't the best move, and queen b6 was, in fact, a better move. And then a few years after that, it was discovered that, oh, no, we were wrong. Bishop e4 is the best move, and queen b6 is actually not good at all. And so today, using an online version of Stockfish on a cluster, it discovers that queen b6 leads to a forced draw, and bishop e4 leads to basically a forced win with +4 for anybody who plays chess. So equivalent to 4 pawns ahead. So what took many, many years to resolve is now resolved in a few minutes with a top program. So that's what 3600 buys you. So back to the graph, I'll make a simplified version. You can see there the picture, and there was an era of approximately 20 years or so, a little more, where computers could be helpful, after which they became unhelpful. It's interesting to also compare with blitz chess, where blitz chess is chess where you have only a few seconds to make a move, say 5 seconds on average. In this case, the cost of managing the collaboration between the human and the computer is so high compared to the amount of time for a decision that the era where computers could actually help in blitz chess was very short, after which computers just were best. So it was only less than 10 years here, as you can see. So the era for effective collaboration was very short. Interestingly enough, in correspondence chess, where you have 3 days for a move, the era of collaboration lasted much, much longer, for decades. And the reason being that there's days to work out how best to use the computer. And humans figured out great ways to use computers beyond what they would do if they were just searching by themselves. So this suggests that to me anyway, that other fields may go through something like this in the long run, where there's a human solo era, a human-led, computer-led, and then computer solo era. And we'll see how that goes. All right, and here's some wild, crazy thoughts of where some of these eras, these technologies fit in these phases. I won't spend too much time on them because I want to leave plenty of time for questions. But so I'll move on from there. We can come back to that if you want. The other one, a second area that I think is very interesting, is interactive games, such as text-based games. Now, these are games that I played when I was in grad school and wasted a lot of time on, I have to admit. Games like Zork and Adventure. And they're very simple games where you see a text description of the environment, and you can type in text commands, and then you see an updated text description based on what you did. And these games were actually quite interesting and very creatively put together. And it turns out that they are, although you can probably train a system to play any individual game, to create a system that can play a new game from scratch is very difficult. And I don't think any system can learn how to play these games because they're so complicated, most of them. So I think there's some really interesting opportunities in interactive fiction games like this. And the last area I'll suggest is in benchmarks. I would say right now that while benchmarks are clearly very important for AI, we rely on them. In fact, we rely on them way more than we should as a field because they have many problems, but you can see here that the benchmarks I show here, ImageNet, Atari, and Squad as one sample NLP benchmark from a few years ago, have all been quite influential in their fields. But benchmarks have a lot of problems. This is just a small subset of the problems. I've got a lot of other presentations that go into this in much more detail. But you can see a few issues with benchmarks that overfitting artifacts, the buying performance in order to do well on the benchmarks, and saturation. The benchmarks that are created now often are created one year and then saturated the next year, and people move on to a new benchmark because it's no longer useful for distinguishing between different systems. So I think that, again, I probably won't go through this in detail, but happy to talk about it in questions. I think games still provide an interesting set of problems for AI systems. I know that a couple of years ago at NeurIPS there was a NetHack competition where NetHack is an ASCII art-based dungeon exploration game. So it's very low on computational resources. It doesn't require graphics cards or anything like that. But it's way beyond the capability of the neural systems or the symbolic systems or the neurosymbolic systems that tried to attack those. So that's an example of a game. The text-based games are another example. And I think it's easily possible to define new games, games based on collaboration, social deduction games, that all pose really interesting problems in the way that I mentioned. So you can see, looking at this chart, again, repeating the chart on chess, there's a lot of room for creating either new games or variations on existing games that move into the yellow and ultimately into the red parts of this diagram that would stress out current AI systems, LLM systems, or RL systems, or whatever. And I think exploring this space in a really systematic way will be very profitable. And in conclusion, I hope I've managed to convince you of four main ideas. Games have been and will continue to be relevant for AI research. There may be some hints in the evolution of game-playing systems that will help inform human-AI interaction in the future. Language games, such as interactive fiction games, have some interesting and useful properties. And if we really care about building generally intelligent systems, we need to think about better AI benchmarks. And I think games can, if not be the only thing, of course, they can have an important role in those kinds of benchmarks. Thank you.
Thank you very much, Murray. There are a lot of questions in the Mentimeter, and you can start thinking about asking the questions directly from the audience. And using the questions in the Mentimeter, I will use popular vote. So the more votes, the more likelier it is that we will ask this question. But there was one question with 16. Okay. Which one is it?
Hello.
I'm just thinking, Murray, if I haven't played chess myself, should I start or should I give up?
It's too late. These days, kids start very young playing against computers and are phenomenally good by the age of 12. In fact, I had the daughter of one of my colleagues visit me at the lab a couple of weeks ago. She was 8 years old, and she was already as good as I was when I was 16, and she's just this tiny little thing, and she's already very good. In fact, the challenger for the next World Championship, was just decided last week, is a 17-year-old from India. So they start young these days.
Okay.
Too late, sorry.
Okay. But the ultimate question that comes together with generative AI, when we think, will the kids will be willing to learn how to write essays when they have ChatGPT? Is it the same with the chess? How do you
That's a really good question. So the fact is that chess is more popular now than it has been ever, partly because of the internet allowing people to play anybody, anywhere in the world at any time, and the training opportunities that are available in courses online and so on. So people continue to play even though computers are clearly much, much better. They enjoy it. It's entertaining to watch. I was watching the candidates tournament that was taking place last week until at the airport on my way here. So it's very entertaining. Writing and some of the skills that we need to learn in school, there's a great temptation to cheat and use LLMs to either do all the work or a lot of the work. And I think that's going to be a real problem for the discipline and the creativity of students. And I don't know what the answer is, but I think somebody needs to think very carefully about how to incorporate that.
Okay, thank you. I'll skip my questions so that they like me. The most popular question is, what was wrong about people's assumptions in 1958 that they so overestimated speed of progress? Any parallels with today?
Yeah, that's good. So back in those days, people were thinking that the best way to create intelligence was to emulate human intelligence. And if you think about how you go about solving a problem, you don't realize all the massive amount of parallel computations that's going on, that's doing pattern matching and idea suggestion. There's sort of the system one kind of thinking that if you know the system one, system two Kahneman breakdown of thinking. They didn't understand the system one part of AI. They knew all about the system two, and they thought about theorem proving back then and chess and all the kinds of logical thinking things, but they didn't understand how difficult it would be to get the system two, the image recognition, language understanding, translation, voice recognition, all those things. It would be many decades before those, and it would take deep learning to really solve those problems. And I'm sorry, and then it goes on, what are the lessons, is there any lesson for today? I think people, this is my opinion, and other people will definitely think differently. I think that LLMs by themselves, just by simply scaling and clever prompting tricks and RAG and whatever things you want to throw at it, have some fundamental theoretical limits on what they can do. And when you tackle problems that require reasoning, and this is the subject of my talk at ML Prague, problems that require reasoning, as we commonly think of reasoning, they tend to fail as they encounter problems that are either novel to them, and they're not, well, novel problems, they will fail if they're not really, really simple. As the problems get more complex, they can go from near 100%. And a great example is some work at Arizona State by Kambhampati and his students. They took Block's World. If you know Block's World, it's a domain where you imagine a table with colored blocks on it, and you're given a start configuration. The blocks are arranged in a particular way, and your goal is to rearrange them to a target configuration, which you're told. And you figure out, if you imagine a virtual robotic arm that comes along and picks up the blocks and stacks them in a particular way and moves them around. turns out that LLMs can do quite well on a corpus of blocks world tasks, probably because they were in the training data, but we won't mention that, the pre-training data. But if you change the names, and they don't call them blocks, but you call them something else, and you don't call stacking, but you call it something else, the performance goes from quite reasonable down to 0. It shows that they can't do the abstraction or the isomorphic, to detect as an isomorphic problem to something it already knows how to do. But because the names have been changed and the way it's been trained on autoregressive training, it just simply doesn't have the capabilities to do that transformation and reason about it.
Another one. Why have best people not improved in playing chess based on the Elo plot, even though they have access to superhuman computer players? What makes it so difficult to transfer the knowledge?
Yeah, so there's a couple of interesting questions there. I think people have improved, and the average, I didn't show a chart on this line, but the rating of the top 10 players averaged has gone up a reasonably large amount over the 20 or 30 years of that graph as people are training. The one problem is that the ratings are not necessarily stable. You can't necessarily compare one era with another era. They're consistent within a particular time, but you can't guarantee a comparison with before. What makes it difficult to transfer knowledge from a chess program? That's a great question. They are terrible explaining what they're doing because they're looking at tens of millions, hundreds of millions of positions to prove that one move is better than another, basically creating a big proof that one move is the best. How do you distill that down to something that's human understandable? You clearly can't. So you have to do something in the way of abstraction and summarization, and nobody's really nailed that one yet. I don't think people have found ways to get computers to explain their thinking other than by very ad hoc means that don't work all that well.
And now for something completely different.
Yes.
What do you recommend to the current bachelor or master's students?
Yeah.
Not necessarily technical.
Yeah, I was thinking about this as my kids are growing up. Now they're now in their 20s, but I was thinking about the question of what professions are likely to be on the upswing and what are on the downswing. And different economists have done studies on this and shown that certain jobs are more likely to be automated than others. But of course, they're missing one factor, and that is that new jobs are getting created that nobody even thought of. Now, whoever thought 5 years ago there'd be prompt engineering as a discipline? That's crazy to even imagine that. So I think you have to carefully consider how easily they automate. But I think if you think back to the computer chess over time, the collaboration eras that I talked about, phases. You want to find a discipline or an area to work where that period of collaboration is going to be as long as possible. And I'm not sure I can give very good advice as to exactly how to tell one that's going to have that property from one that doesn't, but in chess, the classical chess anyway, the collaboration period lasted for about 25 years. So if somebody was able to go into a job that started working with computers a little bit and then more and more, and was able to adapt to the increasing capabilities and maybe turn over some of the work to the computer and trust it on certain things, but know when to verify on other things, and could stay alert and not just be complacent and let the computer do everything. I think those are the kinds of disciplines to think about. I'm worried for some jobs like, photographers, sorry, where you can take you get out your iPhone and take a few shots and send them off to a website, and they'll send you back 100 professional business photos of you that look better than you do in real life on a nice, whatever background you want. It's pretty hard for a photographer to charge, $500 to do a job like that when you can do it for $20 with a generative AI system. So it's, I think coding is another interesting one to talk about as well.
It's actually the best job that I have, because to build an AI community is a job that you probably won't give up to AI. So, yeah.
That's true.
Lucky me. Back to the business. What approaches do you believe could be effective in fostering real-world comprehension for machines? Reinforcement learning algorithms, state space exploration, or other methods?
Real-world comprehension. Would the owner of that phrase care to define what they mean by it? It's understanding is debated a lot, whether LLMs understand what they're saying, and most people that I know say a little tiny bit, maybe. They've constructed this huge matrix of words referring to other words, which refer to other words, and it's all just words, and there's no connection to the real world in any place. There's no grounding, as sort of classical AI would put it. I think it's interesting to think about training in multimodal systems, and then learning from videos, and maybe starting to make the connections to the real world. How this word actually means something in the world, even though I know I can say an apple is red and it's round and it can sit on a table. Those are just words that I'm saying. I'm speaking as an LLM. But if I know that there's some red pixels in an image and they have this shape, and I can connect them somehow, maybe that's a step towards grounding, which I think is essential for understanding.
What do you think about the idea that thanks to AI and its greater impact on society, we are facing a general dumbing down of humanity?
Yeah, that touches on the problem we addressed before of students relying on LLMs to help them write their term papers or whatever. Let me give an example from chess, because I think it's quite instructive. There was this famous game that once world champion Vladimir Kramnik played, where he had studied with a computer a particular opening that he was going to be playing against an opponent. And the computer had led him down to this fantastic sequence, and he found that in this one position, here's the winning move. And he memorized this, and he looked at it, and it said, not only is this the winning move, this is the proper continuation, and this is how you win. And so he memorized that, and then when he sat down to play against his opponent, and this variation came up that he'd prepared, well, luckily for him, so he played down to this position, and he played his decisive move, and he was very pleased. And his opponent responded with a move that he hadn't considered. Now, he knew that this was a bad move, because the computer had not even mentioned it, so it must be a bad move. But he didn't know why it was a bad move. He couldn't, it was so complicated, he couldn't figure out why it was a bad move. And so he ended up losing the game, I believe, because he couldn't figure out what was, quote, obvious to the computer. It was just beyond what he could. So he became complacent. He trusted an AI system to make a decision for him without fully understanding why it was suggesting that option. And that, again, brings up the need for AI systems that can explain themselves in human understandable terms. Some things are too complex to explain, I admit. You know, some mathematical theorems no human is going to understand. There's some chess positions that no human is really going to understand ever. I think it's just beyond human capability. But if you're going to, you know, trust a recommendation or a decision made by a computer, and it's a mission-critical decision, either in a chess game or on an aircraft or whatever, you better darn well understand exactly why that decision is being proposed.
A tough one now. Can you provide a concrete example of a major breakthrough in AI that came from the study of games? It seems to me that fundamentally all major useful breakthroughs came from somewhere else.
Fair point. I think I will freely admit that I looked after we'd finished Deep Blue and trying to look for applications of the Deep Blue technology that we'd built to other disciplines, other than games. And I admit we couldn't find anything that was really very realistic. I think as you move, the reason why I think games are useful, and you can think of the learning, the work that's been done in the 2010s with poker and Go and Atari. I think big breakthroughs in RL happened because of the Atari environment, which helped drive games forward. And those were then also poker, which some in this audience know very well. That's an imperfect information game, which requires different kinds of technologies. Now, do they translate to the real world? Not directly, but remember that picture that I showed. Let me go back to that if I can. I don't know if it's still...
You can.
I think searching and evaluation and reasoning and all the things that Alan Newell talked about can all be important for games. And as we've approached them, these in Deep Blue and many of the other current approaches, we haven't really fully exercised the systems. But I think this provides a template for how you move forward in AI, how you can move into the yellow and then eventually the red part of this space by making games that are more complex. And we still get all the advantages from games that I mentioned at the beginning, but we can systematically broaden that. Now, will these deploy to the real world in a good way right away? I don't think so. But I would argue that LLMs are, while they seem to be very impactful, are they really changing the world in a 100% positive way? Are they generating huge economic benefits for the companies that produce them? Well, they certainly get a lot of mind share, but I don't think it's a profitable business at the moment to run a large LLM because of just simply the cost of running these systems. So I think we still have to figure out how LLMs are going to make money as well. So that's a partial answer. It's a complicated topic, though. I agree.
Can you share some fun facts from the development of Deep Blue? It's a chess player asking, I guess.
Yeah, it was. We started in 1989 by we had a system called Deep Thought, which is a system we had developed at Carnegie Mellon University. And that was our first crack at Kasparov. And we knew we weren't ready, but it seemed like a fun thing to do. So we took them on, and we lost fairly decisively. It was just a two-game match. But I think IBM was very interested in what they saw, and they hired a group of us to come and build Deep Blue. When many of you don't know the details of what happened during that match, but and that's yet another talk that I give. But during that match, particularly in the game 2 that I spent so much time on, which Deep Blue won, that really upset Garry Kasparov. He accused us of all sorts of nasty things, and it took him many years to get over that loss. I think finally about 2015, so 20 years later or so, he acknowledged that he probably lost fair and square. He still wasn't happy about it, and he still was mad at IBM, but he finally acknowledged that he had lost, and that it was his fault for choosing the crazy thing that he did in that last game of the match, which caused him to lose the match. Interestingly, that line of play, and here's the fun fact. In that game 6 of the match, the final game of the match, it was an opening that Kasparov chose because it worked against other programs of the day. It forced the computer, be it Deep Blue or another computer, to sacrifice a knight for a pawn. And computers of the day, other than Deep Blue, didn't handle that situation very well. They scrambled around trying to get their pawns back, and they didn't like being down. Deep Blue loved the position. It thought it was, raining down fire on Kasparov's king, and it was, everything looked great, and it didn't scramble to try and get pawns back. It just pushed the attack as hard as it could, and it ended up being Kasparov's shortest loss in his career, as far as I know.
Any questions from the audience, actually? You can raise your hand. I think it'll be shortest route here.
Comparing current top chess engines, why do you think that it is so hard to reproduce the results of AlphaZero, and why Stockfish is still reigning? I mean, partly maybe because of the neural network, but there was this attempt with Leela Zero, trying to reproduce the AlphaZero, but nothing really, I guess, still came close to.
No, I think to the contrary. I think the reproductions of AlphaZero are actually extremely good and very strong, and I would conjecture are at least as good as AlphaZero, because so much work has been put into them by an open source community and by distributed training. Now, they admittedly DeepMind threw a huge amount of compute power at the problem, and so maybe they trained it better. But after several years of people working on it, I suspect it's already better than AlphaZero.
Murray, are you fine with taking some more questions? There are so many in Mentimeter.
Sure.
Yeah. Any more questions from the audience? Those VIPs in the first row can actually also ask questions.
Thank you for the great talk. I'd like to ask, what are some of the top problems that you and your neurosymbolic lab is working on?
Sure. So I think the two main projects that I'm working on, well, there's three. One is around evaluation of AI systems. As I mentioned in the talk and alluded to earlier, I think benchmarking is broken in AI. We do have a set of standard benchmarks that people use to compare particularly LLM systems, and they're useful in a way because they at least allow some comparison, but they're not very systematic. They don't really test the capabilities of the systems in a systematic way. And I think a lot of work needs to be done. The talk that I gave at ML Prague talked about how do you actually evaluate the reasoning capabilities of these current crop of LLMs. And I think although they behave as though they can reason sometimes, there's plenty of evidence that in fact they're not really reasoning in the way that I defined it anyway. And that some new ideas are needed to create benchmarks that really bring that fact out, that they're not doing that quite right. So that's one part of the work. Another is a particular kind of reasoning, compositional reasoning. Taking, you show an AI system the basic elements of a problem and how things get combined and the primitives. And then it should be able to compose them in interesting ways and tackle problems. So a simple example, you show it how to do addition of numbers, small numbers, and maybe 2 or 3 digit numbers. And then it should be able to extrapolate to arbitrary lengths by learning the algorithm for adding numbers. And then it's called productivity, actually, the technical term. Extend that to arbitrary lengths, and they can't do that. Sort of the recursive kind of thinking is missing from these systems. So there's lots of things that they can't do. So that's another piece of work that I've started working on. And I'm also working with neuroscientists on trying to come up with new ideas for AI architectures that address some of the limitations that we see in transformer-based systems. And one particular lack that we see is long-term memory. And I could maybe talk afterwards, after the questions are officially over, a little bit about why I think memory is an interesting thing that isn't solved by just making bigger context windows or by RAG or other techniques like that.
Okay, let's take this one. Are there any new AI paradigms, learning methods with potential to beat current chess engines?
Potential to beat current chess engines? No, I don't know of any. I think there's 2 paradigms that are the AlphaZero paradigm and the classical paradigm, as evidenced by Stockfish, and they both play at an amazingly high level. I don't know how much room there is above to get above those. There's presumably some room because they lose once in a while. But both kinds of systems play 3600, 3700, 3800. Who knows exactly how well they play, and that's just incomprehensible to humans. They just do things that are they see things so easily that are just beyond human understanding.
Like this one. Do we have a model that would beat humans in more than just one specific game?
Yeah, that's great. I think having a general game playing system that could play any game, you give it a description of the game and it could play it. I think there's some open source systems that would allow one to easily experiment with that. Maybe I don't know if maybe it was DeepMind that put something out, but I think that would be an interesting series of experiments to do, a general game player.
Oh, sorry, I actually skipped that one. What was it about? Can't
I
remember.
didn't see it.
Sorry for that. Is there? I will try to look it up. Maybe I just didn't like the question. Is there any parallel between the progress of AI on chess that we would apply on the today's LLM progress?
Good question. I think the one that I'm most interested in is the collaboration type issue, where you try and work together with an LLM to solve a particular problem. Maybe it's a programming problem, maybe it's a writing problem, maybe it's something else. And there are these, as I said, there were these different phases where the style of collaboration can vary over time depending on the strengths and weaknesses. So I think that's going to be a common model in many industries going forward, is people working together with LLMs or more specific kinds of systems that for a particular industry, working together in concert and working out the best way to collaborate. I think that's an interesting problem.
Okay, if you remember the question that I just deleted, so you can ask it directly from the audience, or there can be another option for a question from the audience, if there are any. No, so let's take a few more. Oh, there is one.
I think like you often say that kind of like what's missing is reasoning, but yes. I've like yet to hear a sensible definition of what people actually.
I can bring up my other talk if you're interested. I do try and propose a definition which is not satisfactory, but it's a step. In fact, I'm going to just do it. Nobody can stop me.
I just wanted to say that we are about to finish and
I've got a whole nother talk here.
Murray, when is your flight?
6 a.m. tomorrow morning. So here's a weak attempt at defining reasoning, but I'll fully admit that it doesn't work right. But so I list a few definitions that I think are quite interesting, and then I try and see what's common among those definitions. And so what I ended up with is, I used as known facts, employing systematic processes to derive new facts to inform decision making. And you can see the definition there. I put to inform decision making in parentheses because that's not an essential part of reasoning, it's how reasoning is used. So the reason why this doesn't quite work is imagine an LLM that has a big context window, and you call the tokens in the context window the facts about the world. And then it does a systematic process. It runs through the layers and outputs a new token, which is a new fact. Now, it's a token, but if you want to call it a fact, you can. It's a new token. And so that's why I'm not quite happy with this definition, but I don't have anything better yet. This is a little more useful, looking at the different kinds of reasoning. There's, deductive, inductive, and abductive, which I won't go through in detail here, but you know it when you see it. Put it that way. You know reasoning when you see it. And in spite of the fact that I can't fully define it, the fact that, let me just put a stake in the ground and say, I think that abstraction is going to be a key part of reasoning. And that's what gives it its power. And again, abstraction is another thing that's very hard to define, but maybe it means ignoring certain aspects of a problem and creating a class or a family of things that are all similar. So that's just a little bit of flavor of some of the stuff that I talked about at ML Prague.
Okay, one last question.
Yeah, maybe a provocative continuation on top of that. So maybe isn't one learning from the whole chess journey the fact that maybe we don't need reasoning, like the same way that the programmers at the beginning of solving chess thought that they need this different kind of, yeah.
So I think I've got you there because I define search as reasoning. So it's by definition, the definition that I use, it is only reasoning. It's so Deep Blue was a reasoning system. Because it's the reason I say that is because it's constructing a proof. It's constructing a proof that one move is better than all the others, and there's some heuristic stuff in there because it's evaluating, using a heuristic evaluation. But it's still, nonetheless, constructing a proof, and a proof is by definition reasoning. Okay.
Thank you. I feel that we could go on and on and on, but we should move on to the informal part of the evening. When we talk to a general public, all of us here in Czechia and all over the world, we usually use the Deep Blue case to explain how AI was developing. So it's a great honor for us that we actually now say that we talked to the guy who was behind it. So thank you very much, Murray, for coming and for spending the evening with us and for the patience with the questions. There are so many of them. Thank you very much for asking the questions and for being such a lovely audience. You can actually, all of us, use the QR code on the badge to give us a feedback. So, Murray, you can use it to give us the feedback on the evening and on the audience, and vice versa. I have a symbolic gift for you as a thank you, and now it makes you actually the Prague AI ambassador.
Okay, thank you.
So, huge applause, please.
Thank you.